Welcome to The Explainer. If you're the kind of focused learner who absolutely loves understanding how things tick at their fundamental, physical foundations, well, you're in exactly the right place. Today, we're diving deep into the absolute physical limits of modern computing. We're going to look at how physicists are literally ripping up the rulebook of traditional electronics to create tech that operates at speeds and efficiencies we honestly used to think were impossible. So, let's just jump right in.
It's a serious question, right? We've all heard of Moore's Law, the idea that we can just infinitely shrink transistors and pack more of them onto a chip. But the reality is, traditional semiconductors are hitting a massive physical brick wall right now at the 1 to 10 nanometer scale. When components get that impossibly tiny, electrons start jumping across barriers where they definitely aren't supposed to be, and that creates massive heat and data errors. We are physically running out of room. So, how do we keep advancing?
Well, the solution to our big data and AI energy crisis isn't going to be found in traditional charge-based electronics. Instead, scientists are looking right at the bleeding edge of magnetic physics. By harnessing the deep, hidden quantum mechanics of magnetism, we aren't just making, small incremental upgrades here. We are entirely rethinking what a computer bit even is.
Which brings us to Section 1, the limits of modern memory.
So, according to the laws of thermodynamics, specifically the Landauer limit, erasing a single bit of information should theoretically take an incredibly tiny amount of energy. We're talking right around 1 milli-electron volt. Tiny. But in the real world, our commercial magnetic random access memory chips, or MRAM, they waste massive amounts of energy trying to switch bits at high speeds. They rely on pushing these large electrical currents, which creates this terrible parasitic energy dissipation we call joule heating. To put that into perspective, we're operating many, many orders of magnitude above that ideal Landauer limit just to keep our server farms from crashing.
So, let's do a quick mental reset here and define the real hero of our story today, spintronics. Instead of just moving an electron's electrical charge around, which again creates all that wasted heat, spintronics uses the intrinsic spin of the electron. Think of spin like a tiny, built-in compass needle pointing up or down. By using these spin states to read, write, and store memory, we can theoretically build vastly more efficient computers. And right now, scientists are upgrading spintronics in two totally groundbreaking ways.
Let's look at that first path in Section 2. Enter the Altermagnet.
This brings us to altermagnetism. Now, this is a discovery so massive, it was actually named one of the top science breakthroughs of 2024. For almost a century, we basically thought there were just two main types of collinear magnets: ferromagnets, like the ones holding up photos on your fridge, and antiferromagnets. But altermagnetism, it's a third, completely unique class. It features something called D-wave spin ordering. Without getting too bogged down in the heavy math, what you really need to know is that this phase combines the absolute best properties of those other two types into something completely unprecedented. This comparison directly showcases the massive value proposition of altermagnets. So, ferromagnets are great for reading data, but they produce these messy, stray magnetic fields, which means you can't pack them close together without them interfering with each other. Plus, their switching speeds are stuck in the relatively slow nanosecond range. Altermagnets, on the other hand, produce zero stray fields. That means you can pack them incredibly tightly, and their unique internal physics allow for lightning-fast terahertz switching. They basically eliminate the scalability limits and the slow speeds of our current tech all in one go.
Moving on to Section 3, spintronics at terahertz speeds.
Okay, so how do we actually compute with an altermagnet in the real world? The mechanics here are just brilliant. Because of their unique crystal symmetries, altermagnets naturally create something called the spin splitter effect, or SSE. This generates pure spin currents without needing any heavy, expensive elements, and it enables giant magnetoresistance, which is the tech that reads our hard drives, but completely without those annoying stray fields. Even better, this works in insulating materials, not just metals. By using insulators, we can switch magnetic states using electric fields rather than electric currents. This absolutely slashes that parasitic joule heating we talked about earlier. We're talking about ultra-fast, non-volatile memory bits that barely generate any heat at all.
Sounds pretty perfect, right? But scientists are greedy for even more efficiency. And this brings us to the second path physicists are taking. What if we change the trigger entirely? What if we don't use magnetic fields, and we don't even use electrical currents at all?
Let's explore that in Section 4, the need for speed. Right now, standard optical switching usually takes anywhere between 50 to 500 femtoseconds. For context, a femtosecond is 1 millionth of 1 billionth of a second. Fast, right?
But for the ultimate computer operating at the very edges of physics, it's still too slow. To break through these final limits, physicists are attempting the impossible, reaching the attosecond scale. They are trying to achieve a first-order virtually instantaneous interaction directly between a pulse of light and the magnetic spin of an electron.
Which leads us to Section 5, Petahertz Clocks and Lasers.
Welcome to the wild realm of petahertz clocks and lasers. This is where we look at the actual mechanics of the ultimate speed trigger, ultra-short near-infrared laser pulses operating on timescales so incredibly brief they're kind of hard to even conceptualize. The crucial mechanism here is called ISTR, or optically induced spin transfer. Think of this as the physics engine making the petahertz dream a reality. When you shine a highly specific near single-cycle laser pulse at a material, the electric field of that light literally grabs electrons and dislodges them across a material interface. As the electrons move, they carry their spin right along with them. And all of this happens coherently, in sub-femtosecond timeframes. It's just wild.
Let's look at exactly how they prove this in the lab. Notice this tiny microscopic sandwich. It's a multi-layer setup of magnetic nickel and non-magnetic platinum. They hit this exact stack with near-infrared laser pulses. Because platinum is a heavy metal with strong spin-orbit coupling, it acts as a highly efficient spin absorber. The laser instantly excites the electrons in the nickel and they just flood across that boundary into the platinum, taking their magnetic spin away from the nickel layer. And we can actually see it happening right here on these charts. Look at the blue lines on the left graph. That represents the magnetic moment of the nickel-platinum multilayer. Notice how it plummets immediately in perfect synchronization with the green wave of the laser's electric field? Now check out the graph for just the bulk nickel without that platinum interface. The reaction is way slower, bogged down by the slow dynamics of the crystal lattice. The interface is the absolute key here. The reaction in the multilayer completely outpaces the slow physical limits of the crystal itself.
So, the main takeaway here is the sheer, definitive proof of concept. The charts show an immediate loss of over 40% of the magnetic moment. It features a sub-femtosecond response time, with a coherent time constant of exactly 4.5 femtoseconds. Guys, this isn't theoretical anymore. This is direct, hard evidence of attosecond magnetism. We now know for a fact that all optical coherent magnetic control is physically possible.
And that brings us to Section 6, the future of computing.
So where does all this leave us? Imagine a world where these two massive breakthroughs perfectly merge. We're talking about combining the perfect, heat-free, scalable materials, like those newly discovered altermagnets, with the ultimate instantaneous speed triggers, like the petahertz near-infrared lasers. This combination would give us light-wave-gated coherent spin transistors. They do exactly what your phone or laptop does right now, reading and writing ones and zeros, but millions of times faster, and using a fraction of the energy. We are literally rewriting the limits of technology.
It really shifts your entire perspective, doesn't it? As we push right up against the thermodynamic limits of the universe, the old ways of building electronics just aren't going to cut it anymore. We're entering an era where data is manipulated by the direct interaction between a wave of light and the quantum spin of a single particle. So the question is, are we ready for computers built entirely on light and hidden quantum magnetism? I really hope this explainer has sparked your curiosity to keep exploring the incredible world of quantum spintronics. Thanks for learning with us today.